Is Anza Ramabulana from the University of Johannesburg, who will speak on the metabolomics and computational tools to characterize the chemical space of Momordica plant species. Please go ahead, Anza.
Hi, everyone. Can you see my slides?
Yes, we can, and we can hear you.
Okay, so my name is Anza Ramabulana, and today I'll be presenting to you guys part of my PhD study titled Metabolomics and Computational Tools to Characterize the Chemical Space of Momordica Plant Species. This is the outline of my presentation today. And Momordica plant species are nutritional and medicinal plants that fall under the family Cucurbitaceae. These plants are phytochemically rich. However, their metabolomes have not yet been fully characterized, especially the metabolome of Momordica cardiospermoides, which has not been reported in literature before. Right, metabolomics has been used for some time now to illuminate different metabolites in different plant species. And this just shows you the metabolomics pipeline on how metabolomic studies are normally carried out. To generate metabolomics data, routinely tandem mass spectrometry is used to generate spectral data that are characteristic to different metabolites. Considering that under collision-induced dissociation, the reactivity of molecules is based on their different functional groups and their structural architecture and their chemical stability. As shown in figure 2, you can see that those molecules do share fragmentation similarity, but their fragmentation does differ because they have some structural differences. Data-dependent acquisition can be used to generate MSMS data, which selects peaks that are greater than a predefined signal threshold for automated MS2 fragmentation. Such studies normally generate very high complex data that are still very difficult to annotate and to interpret, hence the need of a continuous development of computational tools to assist us in the interpretation of these data sets. Such computational tools can also be found in the GNPS ecosystem. In this study, we're going to be exploring classical molecular networking, which groups structurally, can you see my cursor?
Yes, I can.
Which group structurally similar molecules into molecular families as shown in A. The molecules that are grouped into molecular families share fragmentation similarities in their gas phase reactivity. And then to complement results that are found in molecular networking, we also explored some in-silico computational tools, and these results were then put together using a tool called MolNet Enhancer, which then shows us the different chemical classes in our groups. Once we've annotated metabolites, which is highly supplemented by the built-in spectral libraries in GNPS, we then mapped the annotated metabolites into their biological context by doing pathway analysis. So the key research aspects that I will share with you today of this study is on how data-dependent acquisition parameters such as intensity threshold and collision energies affect the molecular networks generated. And then we continue to explore and apply these computational tools to characterize the metabolomes of 4 Momordica plant species. And then once the metabolites were annotated, we then mapped into their biological context. So the methodology that was followed the basic metabolome pipeline, whereby we went and collected 4 Momordica species, Balsamina, Momordica cardiospermoides, and Carankia and Futida. It is important to note that Momordica cardiospermoides metabolome has not been reported anywhere else in literature. So we then extracted the metabolites using 80% methanol, and then the data acquisition was performed on an Shimazu LC-MS 9030 quadruple time of flight on a C18 column, and the mass spectra was generated using data-dependent acquisition. The generated data was then interrogated and mined on the GNPS ecosystem, and the annotations were also then complemented by visiting different databases and spectral libraries. And we then mapped the metabolites that were annotated into their biological context by doing pathway analysis and comparing their relative quantification across the different plant species. So prior to us going into the annotation of the metabolomes of the 4 Momordica species, we went through parameter optimization of some data-dependent acquisition parameters. The first parameter that we looked at was signal threshold, which just defines the threshold that an MS1 peak should reach for it to be selected for MS2 fragmentation. Once that is so how we approach this, we set 5 intensity thresholds: 1,000, 5,000, 10,000, 20,000, and 40,000. And then we use those data sets to generate molecular networks, which we comparatively looked at, and we described how the different parameters were affecting our networks by looking at different indicators, such as the total nodes that were in the network, the self-loop nodes, which are nodes that couldn't be matched to other spectra. Thus, the relationship couldn't be formulated between those nodes. They couldn't form a molecular family like this one shown in B, and nodes that could form a molecular networks, and the identified nodes that were matched to the different spectral libraries that are housed within GNPS. So we then looked at how those particular networks were then performing, which we could see here that the threshold of 5,000 was comparatively giving a much more comprehensive network with much more nodes in the particular network, and more nodes being able to be matched to each other, and also a little bit higher of identified nodes, although the identified nodes are not that much different. And also we can observe that when you compute a network with a combination of different intensity thresholds, you then generate a much bigger and much more comprehensive molecular network. And then the second parameter that we looked at was the collision energies in which the different precursors were fragmented, and we looked at 30 electron volts to 70 electron volts, and the comparative analysis showed us that when we use lower collision energies, we get much better networks than when we use very high collision energy. We start losing some fragmentation information, and thus the networks that are formed are much smaller, as shown in B, where 70 electron volts was used. But now when you compute a network with a combination of different collision energies, you then build a much more comprehensive network, which is much bigger, has more nodes, has more relationships established between your MS2 spectra. And as you can see in D, we also looked at the different spectral counts. So the colors represent spectral count, just showing you the presence and absence of metabolites when now you are using different collision energies. And we can see that if you are to just choose one collision energy, you might miss information about another particular metabolite. So using a combination of collision energies is much better when it comes to computing your molecular networks. And if you are in a crunch and don't want to collect such huge data sets, using using lower collision energies is much more favorable. So this here is just a summary of the comparative analysis of the different parameters that we optimize on different ionization modes, on positive and negative ionization mode, and we can see that the results are quite consistent through the ionization modes, as using lower thresholds is much better. And with the negative ionization, we saw that using the threshold of 5,000 yields a much more comprehensive network, while still a combination yields a much more comprehensive network, and similar observation for using different collision energies. So for the analysis of the 4 Momordica plant species, we then continued with the lower intensity threshold and the lower collision energy, which then now gave us a much more comprehensive view of our metabolome. As we can see here, the computed molecular network yielded many various molecular families, of which we could now see different types of metabolites that are within the 4 plant species. And one molecular family that we observed was that of different flavonoid, and the spatial arrangement of metabolites within this particular molecular family. We could now start seeing that the subclusters within our clusters that are dependent on the different aggregates of which these metabolites arise from. As we can see on top, that our flavonoids are cyanidine and delphinidine based, and then we see the quercetin and camphorol metabolites somewhere in the middle, and the isoramnitine metabolites only one maritime metabolite that was annotated there. So such information now then helps us in the identification of other metabolites that could not be matched to our spectral libraries, or when now you want to annotate a metabolite that has not been reported elsewhere. This type of information can now be informative in trying to elucidate the different metabolites that are within your plant species. Also, one key observation was that this particular species, Momordica cardiospermoides, which has not been reported anywhere else, was the only one that was producing the cyanidine and delphinidine anthocyanins that are within. They are only found in that particular species. So this species can be a good source of such metabolites. And also to now then complement the results that we got from the molecular networking, we explored different computational tools such as network annotation propagation, which ranks different annotations of metabolites in them to aid in it complements your annotation. And then we also did unsupervised substructure annotation by MS2LDA, which shown here on the left. You can see for isoquercetin that the structure that was annotated by network annotation propagation is shown there, and then the substructure or the MAS2 motif that is indicated there is a quercetin related motif which is characterized also by a loss of a hexose moiety. This information complemented and put together using MolNet enhancer now gives us a broader view of our metabolome, showing us that these 4 species contain different types of benzenoids, a lot of lipid and lipid-like molecules, and other phenylpropanoids and other many more metabolites. So this type of computation now helps you to get a view of your metabolome, what actually is what actually is in your plant. And then by using the different computational tools, we're able to annotate, putatively annotate 100 metabolites, which are characterized by a lot of phenylprepanoids, your flavonoid glycosides, and a few hydroxycinnamic acid derivatives, and also lipid-like molecules, which are consistent of terpene glycosides, your glycerophospholipids, and your triterpenoids. So here we just showed that it is very important for you to first go through parameter optimization before computing different molecular networks to get a comprehensive picture, and that the different computational tools now aid in annotation of metabolites and giving us a much broader view of our metabolomes under study. Once the metabolites were identified, we then now map them into their biological context, and we can see that the metabolites that were identified in the study were mapped onto the flavone and flavonoid biosynthesis pathway, the flavonoid biosynthesis pathway, and many more. And indeed, we just showed the glycerophospholipid pathway, of which the three molecules that could be mapped onto that network, were present in all the 4 species in varying relative intensity. That could just show that the species are somewhat different in their genotypes, but they could also just be differences due to the environments in which this these plants are growing in, considering that we went to different locations to collect these different plants. And then we also did some relative comparison of the intensity of some metabolites that were identified in the species, in the different species, and we can see that Momordica cardiospermoides contains a large number of these anthocyanins, which have been shown to have some good effects on cardiovascular diseases and many more. And it also contains a large amount of some sopanins as well. And in conclusion, it is very important that we look at MS parameters before we can generate any conclusive information from data sets, as this affects the quality of your acquired data and your downstream description of different metabolomes. And the use of computational tools does really assist in the unraveling of different metabolomes, as we could get some new insights on a species that we knew nothing about. This Momordica cardiospermoides, we saw that the species had some similarities to the already studied species, but some significant differences. And then tools in the GNPS ecosystem hold a great promise in unraveling complex plant metabolomes, thus filling the knowledge gaps of both unexplored and partially explored metabolomes. And in future, we hopefully will explore the annotation of unknowns within our data sets. And then in future, as I mentioned, we hope to identify some novel compounds within our data sets and to integrate data sets that we've already acquired for location-based studies. So we went to the field and collected these species in many other different locations to see intraspecies differences based on the different locations that they are growing in, and to incorporate other pre and post-analytical parameter optimization data sets to obtain a multidimensional comprehensive view of our metabolomes, and to considering that compound annotation is still a major bottleneck in metabolomics, considering that only 2 to 5% of metabolites are present in spectral libraries. We really need to contribute to building these libraries by providing annotated spectral data. And we hopefully, once this annotation of these metabolites are done, we can then now explore the biochemical framework of the health benefits of Momordica species, looking into maybe molecular docking or doing a few activity assays. And those are my references, and I'd like to acknowledge the University of Venda for housing me, and I can use their instrument over there, and my supervisor and everyone, my supervisors and everyone else. Thank you very much.
Thank you so much, Anza. I do have a question for you.
Yes,
it's from Prof. Duncan Kamati. Did the changes in the parameters affect the number of compounds identified or the quantitation of the compounds already identified?
Okay, so the parameter optimization affected the identification capability of the matching onto different spectral databases, not the quantification of the metabolites.
Okay. Prof. Duncan, I hope that answers your question.
If I may just add to that question, don't you feel that the quantitation is as important as what the actual identification is? Because with metabolomics, we are trying to assess different conditions, or which is the best plant, or which is going to be the most active as a potential medication, etc. So is quantitation not considered an important factor?
Oh, thank you very much, Prof. I think it is a very important factor. And I think for that, I can explore feature-based molecular networking, which then now will take into account my chromatographic information, thus doing a comparison, a comparison of the quantity of the metabolites across the sample. So with the type of networking that we did, it only takes into account spectral counts, which is just presence and absence. But in future, I think it will be very useful to include like feature-based molecular networking, and then now compare the quantity of the metabolites across the different samples and see how that is affecting the results generated. Therefore, thank you very much, Prof.
Okay.
I thought that was well presented, and I think it's an important aspect that a lot of people miss. So thanks for that.
Thank you, Prof. Duncan. Answer one more question. Vusi has a question. What type of activity assays are you planning to do?
So far, I'm still doing I'm still thinking on what type of activity assays that I need to do. First, I will need to first see what metabolites I am saying they are really significant in my data set before I can then decide what type of assays that I really need to do. So if there's anyone who wants to collaborate in such, I'll be willing to take advice.
Okay,